Okay, well, our second speaker this morning is Dr. Hinke Ossinger, who is a reader in mathematics at the Department of Engineering Mathematics at the University of Bristol. She belongs to the Bristol Centre for Applied and Nonlinear Mathematics, and she's an EPSRC Advanced Research Fellow. And the title of the talk this morning is The Mystery of Chaos in the Lorenz Equation. So when we get it, when it comes up.
Oops. Looks good. Okay, thank you very much. Thanks to the organizers for inviting me. It's a real pleasure to give a talk here. And yeah, the mystery of chaos in the Lorenz. Well, okay, I realize it's a bit of a pretentious title, but I hope that I will convey a little bit the reason why I put it up, because really, to me, it is almost like, wow, we are somewhat trying to solve a mystery, and I have this feeling that we're really close to being able to explain what is going on in a much better way than what's been known so far. And so to me, it's very exciting research activity. I'm doing this jointly with Bernd Krauskopf, who's also in Bristol, and with Sebius Duru, who's in Montreal. And for us, it's very much a fun project. So that's how we started out doing this. But it's also in many ways, I think, a very nice way of using applied mathematics. I think of myself as an applied mathematician. I guess you should be a mathematician per se. But we're applying this to pure math problem. So I like the combination very much. And I guess it also kind of means that I'm putting in the middle of a very applied talk and then a more pure talk as the third speaker, but who knows. So I'm going to focus specifically on the Lorenz equations, and I will talk particularly about manifolds in these equations. And so I'll show you a lot of pictures of manifolds, and the whole goal is to explain how the chaotic dynamics is created in such a relatively simple dynamical system. So to start with, let me introduce the Lorenz equations. They're a very simple set of equations, but to my knowledge, nobody has been able to find any solution of it in an explicit sense. So all of this work is done numerically. We know special solutions. You can tell that when you put x, y, z equal to 0, then you have an equilibrium solution. The right-hand side is equal to 0. There are two more such solutions, and they're very easy to find by hand. You can do a lot of things explicitly. But the overall dynamics of this equation is still quite a mystery. So one thing I should point out is if you put x and y equal to 0, then the z equation completely decouples, and so the z-axis is invariant. And there's also a symmetry here that when you have x and y and z at some value, then you could take the negative x and y and the same z coordinate, and you get exactly the same solution rotated by 180 degrees. And so why is this such a mystery? Well, I don't know whether you know the sort of historical background of this. Edward Lorenz in the 1960s was looking at this as a very simplistic model for weather prediction. And what he found was if you integrate a solution, and there's a bit of a picture here, if you integrate this green point here, it's at 0.1, 0.2, 0.3 or so, I believe I used as the initial condition, then you can follow this and you get what's shown here is a time series of the x coordinate only, and you get a switch from x being negative for a while and then switching to becoming positive and then negative again and so on. And then when you use almost the same initial condition, so what I did here is integrate again with that same initial condition just perturbed in the 4th decimal place. Then because of the right-hand side being continuous and everything, you would expect that somehow if there would be a divergence between these two solutions, it would be something gradual. What we see is, well, initially the whole thing is the same because I don't see any purple here, but then suddenly there's a complete wrong switch going on, and then after a while you see that the system is behaving as though these two solutions have nothing to do with each other. And so that was, well, I guess I call it the mystery, but this has been known as chaotic dynamics. And Edward Lorenz really discovered this as part of his investigation of trying to predict the weather. And it's been sort of the primary classical example to try and find out what exactly is creating this chaotic dynamics. Where does it come from? How does the system generate it? It looks so innocent. Where does that actually come from? And I want to explain a little bit on how people have studied this. So when you follow the solution, and actually if you take these two solutions and you plot them in phase space, so you take the x, y, and z coordinates, which is a picture here, then you're getting an object that looks like what this yellow stuff is doing here. So you have this motion where the x coordinate being negative means that you are oscillating on one side with x negative and y negative, and then at some point you switch and you start oscillating with x positive and y positive, and then you switch back and you get this sort of motion. And whenever you switch, that's the unpredictability in the system. You could switch anytime you like almost, but you can never tell which orbit is going to switch when. And so this is known as the butterfly attractor. So maybe you've heard that word. And so there's been this known story that Edward Lorenz was coming to give a lecture and said that a butterfly, when it flaps its wing in Brazil, it could cause a tornado in Texas. And I believed that for a long time until I found out that's not true. He actually, first I was told that it wasn't a butterfly, it was a seagull. And then I found out that's not true either. He had a personal assistant who thought that sounded good, so he made it up as his title, but he never actually used the whole analogy. But it's a good analogy. This little butterfly, something tiny, something in the 4th decimal place, will change the dynamics completely. Now the problem with weather prediction is that this same butterfly or another butterfly can change it again. So it's not like we can predict tornadoes in Texas just because there's butterflies around. Right? That's kind of the annoying thing about it. So where does this come from? Now, this attractor, that's where everything goes. You can start anywhere in space and you will end up on this attractor. So people have been focusing their attention on studying what is going on the attractor alone. And that's, oops, my computer decided to fall asleep. I forgot to set that, I guess. So the attractor itself is, as we found out, is a fractal object. And the way people have been studying this is they've made what is called a template. And so what is happening is you pick a line, you pick a line between these are the two other equilibria. They have the same z coordinate and they're symmetrically related. And you pick a line through those equilibria and you actually focus only on the bit in the middle. Then there are really two parts because we have this invariant z-axis. And so what you do is you follow what the orbits are doing starting on this line. And so here I have a little gadget to illustrate this. So I have my line here, and I'm focusing now on the part where I go from the negative x, say, to the z-axis. And the z-axis is this blue line that is on this piece of paper. And so when I follow my orbits, they go down, and they start this oscillation, and then some will make another turn on the left side, and others will switch over to the right side. And so when you see this stuff coming back, they kind of fan out, and some will make another turn, and others will go over to the other side. But I'm stopping when I'm coming back at the same z-coordinate of my line. And then, of course, we have the other half. So we have another one, and you put these two together, and for that, it's very practical use of a paper clip. So now I have my two halves of the line segment, and they both have this oscillation going. One goes to the left, the other goes to the right. When they come back, they both fan out, and then I stop when I get to the same z-coordinate. That z-coordinate is actually equal to rho minus 1, and since rho is 28 here, it's 27. But that's just for those who like to know the exact numbers. So, of course, this is a vector field. These orbits are not going to come back together exactly on the line. That would violate the uniqueness of solutions. And so what I have is these come exponentially close to this line because of the contracting dynamics that we try to get contracted towards this attractor. And so then the whole process starts all over again, and you get another layer, which is again exponentially close to what you've already got. So the idea of the template is to say, forget about all this exponential closeness, and let's put all these together, just identify them, and put the return exactly back on the line that I started with. That's cheating a little bit, but it's mathematically we call it identification, and then it's fine. Okay. Now this is the difficult part, I guess. Oh well. Let me, in the interest of time, not try to really glue these together, but I have the surface where the two lines are identified with the line that I started off with, and I get this sort of, it's a branched surface now. There's these two bits that come together at the same bit, but on this template, I can try to find out what is going on the attractor, right? It's not quite the same because of the identification, but the dynamics can be described purely in terms of, okay, I start on a particular half of my segment, and then I either stay on that half or I go over to the other side. And you can do the whole analysis that way, and actually there's a whole symbolic dynamics that is associated with that to find out what kind of dynamics, chaotic dynamics is happening. And this whole idea has been used to show that there is chaos in the Lorenz equations. And what maybe I should mention some names. So the Lorenz template, as it's called, is really due to Guggenheimer and Williams, and it's already quite a while ago that they did this in the 80s. But relatively recent, at least I still think it's relatively recent. This is 99. That's 10 years ago now, but it feels relatively recent. Warwick Tucker, as in his PhD thesis, he actually tried to verify that when you do using interval arithmetic, so this was using the computer in his proof, that all the conditions that you need to satisfy in order to be allowed to do this identification, that this actually worked for this set of parameter values. And so he proved that the proof can be applied for this particular case. Perfect. So now the proof is complete if you allow the computer to play a role in this. And so here is a visualization of the template as we calculated this. And so just to give you an idea, it kind of, it's not quite right, the identification. It doesn't quite come back the same way. And so this picture is somewhat trying to visualize that. But it gives you a good idea of this sort of, the attractor itself is really almost like this branched surface, except that all these sheets come back and they're exponentially close together. So this is actually the beginning part of the unstable manifold of these two equilibria. So they have two unstable eigenvalues when you look at the linearization, and these two unstable eigenvalues, they correspond to a two-dimensional surface, a manifold truly, that contains all the orbits that in backward time go to the equilibria. So there's one for each equilibrium. Then this origin down here also has an unstable eigenvalue, but it has two stable eigenvalues, and there's a two-dimensional manifold associated with the stable eigenvalues that form the all the solutions that in forward time go to the origin. So that's the definition of stable and unstable manifolds, in case you didn't know. And so what I really have in terms of my branched surface, or this sort of template idea, down here I also have a stable manifold of the origin, and it sits not quite perpendicular, almost perpendicular. Well, for the case of the Lorenz equations, it's perfectly perpendicular to the this surface that really is somewhat formed by the unstable manifolds of my two other, the non-trivial equilibria. And so this blue little disk, that's to me the point of interest. This thing takes me out in the realm of space other than the attractor. If I start somewhere else, this blue manifold will guide me towards the attractor, And so the way the blue manifold sits in phase space tells me how I'm going to get onto the chaotic attractor. And what is very interesting when you think about that, if I have this sensitive dependence on initial conditions of the chaotic attractor itself, and I start somewhere else in phase space, then at some point I'll reach the attractor. And then suddenly I have this sensitive dependence on initial conditions. So out there, I already must somehow have some special choice to make in order to make my orbit do precisely what I want on the chaotic attractor. If I take 2 points very close together, far away, they go to the attractor, and at some point they'll start to do something differently. So what is it out here that decides that they can do something differently? And out here, it means that there must be a piece of stable manifold of the origin in between these 2 points. However close I choose them, must be a piece of stable manifold. So this is the stable manifold of the origin is an example of a face-filling surface. Yeah, this is like a space. It's okay. What did I say? Space-filling surface is what I wanted to say. So you have a plane-filling curve. This is 1 dimension higher. So this manifold of the origin is really taking the whole thing into 3 dimensions. And so this is the step. And I realize when I look at the time that I have to move on. But this is the step of what my contribution or our contribution to this project is. You have the attractor. We kind of know what's going on the attractor using the template. But how do we get this into the bigger space? That's the interaction of the attractor with the stable manifold of the origin. So, the stable manifold of the origin is also quite a long-term project. There are a lot of people who've been trying to calculate this, and we've had almost a bit of a competition going on on who can get the best part or the nicest picture and whatever. And so it's been a lot of fun with several different techniques. And the technique that we used, that Bernd Krauskopf and I introduced, is based on the idea of radial growth. So when you want to compute a surface that's really starting at the origin, then you'd like to find the surface sort of every bit is as important as everything else, so you start this radial growth. And so it means that you think in terms of having a geodesic distance defined on your manifold, and you pick up the level sets of this geodesic distance function. And so what the algorithm does, it just chooses one distance after the other in a discrete way, and it adds the next level set to the data set that I've already got, and that gives me a good rendering of the manifold. And well, here's an animation of showing this in growth, and at some point the steps become a bit smaller because of the curvature that's somewhere happening locally. The algorithm automatically adapts to what kind of step size it's going to take next. And the level sets themselves are found by continuation of 2-point boundary value problems. And this is actually part of a very well-known famous code that's written by Sabius Doodle. So now you know why the 3 of us are kind of working together. Sabius Doodle wrote a program called Auto, and really what Auto does is solve 2-point boundary value problems. So if you're in dynamical systems, you may think like, oh, but doesn't it do bifurcation analysis as well? And the answer is yes, but in the form of 2-point boundary value problems. Let me go back to the actual task here. So we're interested in calculating the stable manifold of the origin. Here you see a much bigger piece, not just this little disk anymore. But yeah, this is supposed to be a space-filling surface. So, you know, this is only up to geodesic distance of 100, and that's not far enough. I want more. I want the whole thing. How does this relate? And yeah, then we step back. Sort of like, okay, but we're still focusing on 28. But that's where the chaos already is. And I want to know where the chaos comes from. So how does that get organized? And there is actually already quite a lot known. If you fix sigma and beta, and you vary the rho parameter, then you get a bifurcation diagram that's actually very easy to analyze. You get the origin is down here, and so I'm plotting the absolute value of x, I have the origin down here that is stable up to rho equal 1, and then it becomes unstable in what's called a pitchfork bifurcation. And that creates these other two equilibria. And so there's only one curve shown here of how the x-coordinate of the equilibria is varying with rho, but since the equilibria are related by x and minus x and y and minus y, so that's actually 2 at the same time. And these are initially stable, and this is actually the convection that Edward Lorenz was after. These equilibria, they really define the convection in the atmosphere that he was trying to explain. But then when your rho value, which is really a Rayleigh number and it should be a bit higher, is passing a magical value of 13.91 something, there is what is called a homoclinic explosion happening. And this homoclinic explosion, I will explain a little more in detail what exactly this means. This is the creation of chaos. What is happening here is they found out based on the template that then suddenly you get chaotic dynamics. Initially, it is not attracting dynamics, so there is no chaotic attractor yet, but there is chaotic dynamics in the system in the sense that there is sensitive depends on initial condition in an unstable way. And this regime here that is happening immediately after this homoclinic explosion is known as the pre-turbulent regime. Chaotic dynamics is there, but it's unstable. And then it becomes stable here, and rho 28 is definitely in that other regime where the chaotic dynamics is stable. And this happens through what is known as an E to P connection. There is a heteroclinic connection from an equilibrium to periodic orbit. I'm not going to go into details of this. I really want to focus on the creation of chaos, the homoclinic explosion point. So what is a homoclinic explosion point? Well, explosion point, that's to make it sound really cool. The homoclinic is the bifurcation as it's known. What is happening is that the unstable manifold of the origin, which is a one-dimensional curve, is connecting back to the origin itself. And because of the symmetry of the system, it does that both in the left and the right side of these two curves. And so this is the solution that if I go backward in time and let time go to minus infinity, then I end up at the origin. But now I have the special case, if I go forward in time, I also end up at the origin. What that means is that I must be contained in the stable manifold, because the stable manifold contains all the solutions that in forward time go to the origin. So this red curve is contained in the stable manifold of the origin at that particular rho value. And so here is a view of this of the stable manifold where the front part has just been chopped off, so you can see it a little bit. So this curve sits on that manifold and on the other side as well. And here is a view where the manifold has been rendered transparent, and I'm not sure which one you prefer best, but I guess the whole point here is to show that this manifold is on, the one-dimensional manifold is on the two-dimensional manifold. So what exactly does that mean? It means that just before the bifurcation, I miss, and after the bifurcation, I miss. But I miss in a different way. Before the bifurcation, the right side goes to the equilibrium here, which is attracting for this lower rho value, right? It only becomes attracting at 24 point something. And then the left side goes to the left equilibrium. Now, after I've gone through this connection, what is happening is the right side goes and it actually converges over to the left. And the left one goes over and it converges to the right equilibrium. So instead of converging like this, now the system converges like that. And it makes all the difference. And people have been happy with that so far. And it's like, well, where does the chaos come in? How does that work? Now there's one thing that is not shown in this image. At this moment, there's actually also a periodic orbit created, for those of you who really know about homoclinic bifurcations. So there's no periodic orbit here, there is one here, but it's an unstable periodic orbit. It's not like you will immediately see it. So the switching also generates periodic orbit. Well, actually what it does, it generates infinitely many periodic orbits due to this emergence of the chaotic dynamics. So this is where we started, and this is where we wanted to try to find out what was going on. In this picture, I realized that this doesn't come up very clearly. I guess you can almost forget about all the text that's on this picture. This is just to wow you a little bit. I'm taking rho value actually quite a lot less from the homoclinic explosion. This is supposed to be the boring case. This is where there's nothing going on yet. And so what we did was use this method of geodesic distance level set selection to find the manifold, and so this is the first part, and it's really a very big data set already, trying to convey what this manifold looks like. And what has happened here is I've taken out I'm rendering transparent the top half of this manifold. And where exactly I cut is at the plane where my z-coordinate is equal to rho minus 1. So precisely the plane that goes through the two equilibria that sit over there. And so that's to do with this template here, where I have this line that I started off with going through the two equilibria. So that line is contained in that plane. And there's a bunch of other curves here. There's you see a little bit of red of the unstable manifold of the origin that now goes to left and right goes to right. And then there's another curve in here that we found very helpful, but I'll just skip discussing it. It is, for the experts, the strong stable manifold of the other equilibria. But it acts as an axis of rotation for the two-dimensional manifold. So this is what's happening. There is a lot of sheets coming down. There's a sort of helical structure growing, and then as the manifold grows bigger, these kind of fold over and start to kind of hug on the negative part of the negative half of this negative z-coordinate half of this manifold, and there's sort of exponential decay there in how this hugs together. But at this stage, there is no chaos yet. I can pick any point and I will go to either one of these two attractors. So in order to visualize that a bit better, we decided to just look at the intersection curves of this two-dimensional manifold with this plane through the z-coordinate equal to rho minus 1. And so there are two equilibria. There are these intersection dots of the left and the right branch of the unstable manifold. These dots correspond to this strong stable manifold of the P plus and P minus, these non-trivial equilibria. And these cyan curves, they are the intersection curves of my manifold. And I really see a nice structure. The first bit that comes out of the origin is this sort of major intersection line that cuts all the way across. And then I have these others that form this sort of cup-like structures that are either cup up or cup upside down. And just based on this, you can learn a lot about the kind of dynamics that is going on. But really, you can draw this, you can color this. This is kind of embarrassing. Oh, this is really... That is supposed to be pink in here. This is pretty disastrous. Maybe I should turn my computer the other way around. You can sort of, well, I guess you cannot see that either. So this color does not come up very well, I'm afraid. This is really annoying. So this is supposed to be white and this is supposed to be pink, but we can't see that at all. Okay, so this is a major disaster. This was supposed to indicate the different basins of attraction. So you're going to have to believe me that we can do this. We can actually color this in, and so this is supposed to be pink, and this is white, and then this is pink again, this is white, and so on. And so you can have a real good view of, if I pick all my initial conditions, if I'm in pink, I go to P plus, and if I'm in white, I go to P minus. Now, this is going to be terrible if I show you the chaos, because you won't be able to see that either. So here is the chaotic case. And again, this picture is to give a first impression of what is going on. One thing that you see for the rho value that's now larger than the homoclinic explosion, but still inside the pre-turbulent regime. What is happening is I have this first intersection curve, so the first bit is still the same, but then I don't have this other sort of sheets coming down and hugging the negative bit. Everything now seems to curl up. And I get the intersections where the sheet comes down and then it folds back and it curves back up. That's a big difference that's happening now. And if you look at this on the scale of the intersection with the plane, you can see a clear difference between the case we had before and the case we have now. there are still these kind of cup-shaped curves. They are still there, but a lot of them are accumulating now onto the this sort of weird shape that I had here, and there is something similar there. But there are a lot of intersection curves there now. Now, just to confuse you even more, there is no pink in this picture. There isn't, because what is happening now is this is not really separating the two basins of attraction any longer. And so where the chaos is coming from is because my separatrix of the two attractors that I have here, that really is formed by the stable manifold of the origin alone here, is now being pulled into two different separatrices that come from the periodic orbits that are created in the homoclinic bifurcation. So there's these two crosses here. There's a periodic orbit that comes out of the homoclinic bifurcation, and it also has two-dimensional stable manifolds. And you need to take the two together to see what the actual basins of attraction look like. Now, I'm really glad that at least there is some gray showing up here. So this is this idea of pulling apart. At first, I just have the stable manifold of the origin. But after the bifurcation, the stable manifold, if you want, thickens into a channel, and you have the real basin boundary here is formed by the stable manifold of this is, let's think, this is P minus, and this light green one is P plus. And there is a whole accumulation going on here, and this is not just light blue, this is dark green, light green, and the blue. So there are three curves that are all sort of plotted on top of each other, and it's just way too difficult. But the very last one here is light green, and the very last one here, the real basin boundary of this region here, is dark green. And so everything accumulates onto what you could call the primary branch of the intersection of the basin boundary of the periodic orbits. Light green here, dark green here, and then there's a whole mess of light, dark, and blue, light and dark green and blue colors. But this is also in terms of a channel system. So it's always this thickening. Out of the blue curve come these two, and you create this little gray channel. And now what is happening here, yes, I really need to hurry up, is that this is a zoom to try to show you this, where if I look into this accumulation system, I can see this sort of fractal structure popping up. And what is happening here is, of course, we've calculated not the entire manifold, it's infinitely large. We've calculated the first bit. In the first bit, what you can see is already the structure of thickening of blue lines, but not all the blue lines have thickened yet. And so what you need to do is take this whole sort of fractal structure that you get from this round of the computation and think, well, if I would have calculated things further, then I would have had to fill in more of this fractal structure. So it's like you have a middle third Cantor set construction. So you take first a line, and then you take the middle third that you take out. Well, here you take a blue bit, you thicken it, you make this kind of channel. And then inside the channel you have to put more and more of these thickened curves where you then split into, well, this is supposed to be pink and this is white here. So that's where the actual basin of P plus and P minus are. So here we've resolved it. The channels haven't been resolved yet. That's where we have to take another, say, middle third Cantor set construction. We have to take out more to make sure that this is basin of P plus, this is basin of P minus, and here we don't know yet. And then the whole thing gets iterated over and over again. It's a bit more complicated than a middle third Cantor set because I have I have a whole lot already, and the whole thing has to be plunked in each time. So it's an infinite depth kind of process of creating channels, infinitely many of those, and then do that over and over again. So it's like, instead of doing this infinite process once, you have to do it infinitely many times. It's kind of complicated, but the idea is very similar. So the chaos comes out of thickening of the stable manifold. Okay, so I hope I've given you a bit of an idea. I really need to wrap up, I see. There's computational side to this. Really numerical analysis, if you want, combined with manifold theory, bifurcation theory, to help give the two-dimensional analysis of really one-dimensional maps in how the analysis of the chaotic attractor in the Lorenz equations is being done to pull that into the full space of the system, what is going on. And there is a lot more work that you can do here in terms of, well, there are other bifurcations, there are other even homoclinic bifurcations, like a Shilnikov bifurcation, for example, where you might wonder, what is actually going on with the two-dimensional manifolds? Everybody knows how the one-dimensional manifold connects. That's the kind of picture we can draw easily, but what's the two-dimensional manifold doing? And this is not easy. People seem to have thought so far, like, oh yeah, something like this, and then yeah, well, I'm not quite sure, but roughly I can sort of try to sketch it, and then I'm not sure what happens. And so we've started a bit of a project where we investigate what other things are going. There's a PhD student working on that, Pablo Aguirre, and we've also want to try to put this in the realm of say, even more chaotic, hyper-chaotic attractors in slightly higher dimensional spaces, and that's a project that Steffi Hietmeyer will start on in the summer. So, my time is up. I want to show you just a quick bit of the add-on that this whole idea of using geodesic level sets is something that we felt is actually a nice way of visualizing complexity in a simpler sense, that you can take just one of these bands that the algorithm computes and think of that as conveying the chaotic dynamics in the Lorenz equation in a more artistic sense. And that is what actually happened. So we got in touch with the artist Benjamin Storch, and he made out of stainless steel, he made a sculpture of one of these bands of the geodesic level set, or, well, if you want, two consecutive steps of the algorithm that we computed. So using our data, he actually made this sculpture, and just to show that it's real handwork, I'm going to finish with this last slide, that this is Benjamin hammering, and this is the intermediate result that needs another month of polishing so that it's nice shiny steel. And I thank you very much for your attention.
Questions?
Curiosity, how on earth do you specify a curve like that to give to an artist to make?
These are, to be honest, not just two consecutive steps. There are about 10 steps in the algorithm that connect from here down up to there. And they're all given in terms of coordinates on how we calculated it. So they're like 10 concentric circles topologically, and we specify where we start. And you give the coordinates of a mesh that's roughly uniformly distributed on each of the circles. And then Benjamin, who has a PhD in art, and I guess that helped because he got all that interpreted in the CAP program properly, so that he could have the image on the computer in his workshop to the eye match the shape. So that's how it went.
Where's the sculpture now?
Oh, I'm afraid that, yeah, we tried to find funding for the sculpture, but it proved very difficult. So we've commissioned it, and it's at my house. But yeah, every now and then it goes on show. So it's been, yeah, well, it was exhibited first time in Cardiff, and it has been in the Netherlands at a conference on bridging mathematics and arts.
Any other questions?
After the computation, I can have the computer graphics image. In your case, if you could have the same image in your head at first or not?
Yeah. There's always a bit of, if you're a mathematician, then for some people that means that you can do things in your head that other people cannot even do on paper. And I think this is getting to the realm where also mathematicians fail to do it in their head. So what I think my visualizations are really important for is to help the brain a little bit towards this is how you should think about it. And this actually ties in with when 15 years ago when we started this computation of the Lorenz manifold, the first question really was, what does this look like? We have a manifold that is supposed to go up and it cannot just pass through the attractor, so it has to start folding up and spiraling, rolling up around the one wing and the other wing. And if you think of doing that with starting with a disk from here, this one goes this way, this one goes that way, you'd like to have it tear in the middle. And so how can it not tear? How does that work? And so you can try, think about that. And people have done, there have been sketches in the late 70s by Perello from Spain. He's tried to sketch it, but he already used the computer to guide his thoughts in trying to sketch what was going on. And these sketches have been reproduced in the famous Geometrical Behavior of Dynamical Systems books by Abraham and Shaw. But yeah, it's a help.
Image was so impressive among the physics people. So impressive. This is the first image among the physical persons. They were so shocked.
Yeah. Yeah. This is and this is precisely why I'm doing this. This is to visualize what is going on, and we thought we understood this, but by seeing the pictures we realize it's a lot more complicated than we thought.
Thank you very much.